Mechanical engineering is all about the heat. There's no such thing. There's no such thing as coolness. Okay. What it is lack of heat. If you got cold air blowing on you, it's not putting cold on you. It's absorbing heat out of it. Okay. So the way we describe heat is a BTU. It's the amount of energy to raise a gallon of water 1 degree.
That's it.
So it's a small amount. It's approximately equal to a match. That's a BTU of heat. So there's 12,000 BTUs in a ton of cooling. Okay, at your house, you know, you have that thing outside that blows air out of the top. What?
When you say ton, do you mean weight?
No. I'll get around to defining that.
Okay.
Exactly. It's just an amount of cooling. And what it is, it's not really cooling, it's how much heat it sucks out of the house. Okay? So a ton of cooling is 12,000 BTUs. And your house can have, you know, it's got the thing outside that blows air out of the top of it. Y'all know what those are? The condensing unit on the outside of the house that blows the hot air out of the top of it. That's the outside part. Then the inside part is the air handler, and that blows the cold air out of it. Those are air conditioners, and they come in tonnage sizes, either 1.5, 2, 2.5, 3, 3.5, 4, or 5 ton, depending on the size of the house. This is what a mechanical engineer looks at. Where's the heat going to go in the wintertime? How does it get out of the house? When you put the heat in there, how does it get out? Or in the summertime, when you put the cooling in, that's really not the way to say it. It's how does the heat get inside the house in the summertime? Okay. And it can go out through the roof, through the wall, through the window, through the door, and through the bottom. And when somebody calls me up and says, what size air conditioner do I need for my house? And they want to build a house and put an air conditioner in it. I have to run a load, basically count the windows, measure how big the windows are. That lets out so much heat and lets in so much heat in the summertime. You know, if you've got insulation in your attic, you know, if it's just a little bit, that lets out more heat than a lot of insulation. Okay, same with the walls and everything like that. So that you measure how many BTUs of heat you're going to lose or gain, and then you add that up, and that's how many tons of air conditioning you need. Okay, so okay, when you're building a house, you have to read the code book on a lot of different things. This page in the code book tells you you have to use R30 insulation in your roof if you build a new house. That's a law. If you try to do anything less, then the code inspector will not allow you to occupy the house or the building. So we look at the code books and design the house, and then I run a load on the house and tell them what size air conditioner they need. This is what I was talking about earlier. You have the heat pump outside and the air handler inside and the ductwork that goes all around in the house. I want you to understand this and get this picture in your head. This is blowing hot air. In the summertime, this thing blows hot air out of it. It's sucking the heat out of the house and blowing the hot air out here, and so the air in the air handler is cold. And that's the way it works. I know that sounds like a funny way to describe it, that it's sucking the heat out of the house, but that's exactly what happens in all different kinds of air conditioning systems. And I'm going to show you how, like a geothermal system. Good question. That's the thermostat. The thermostat is on the wall, you know, when you raise and lower it, and you set it on 75. and it's got a thermometer in there. When it measures the air in your house at 76, it says, uh-oh, I'm getting warm, turn on. It tells it to turn on. Then it turns on, it blows cold air out, and then the thermometer measures, and when it goes down to 74, it says, I've achieved what I need to, so turn off. Okay, that's a good question because each split system only gives you one thermostat. So if you have, let's just say you have a 3-story house, and you say, well, I just want to get one air conditioner because it's cheaper. You only get one thermostat. So let's say you decide to put it on the first floor. Well, heat rises, okay? So the cold air is coming out, the heat rising up the stairwell, and the guy on the first floor is comfortable because he's got the thermostat. But the guy on the second and third floor, they're getting hot because they don't have a thermostat. So that's a big problem in design and in buildings, is not having enough thermostats. And I want to talk about, that'll lead you towards what they call VAV, and I'll explain that in a minute. That gives you more thermostats. That's what an air handler looks like up in the attic, with ductwork connected to it. And in engineering, a big part is doing details. You draw the details out and put them on your drawings, like on that drawing over there. And I've spent so much time on this one single detail, just getting it right, just playing with it and changing things, and then a contractor will build it and he'll say, the frame you got is too expensive, you know, it's ridiculous, so I'll change it. But I think I got this one right. That is a detail for how to mount an air handler in an attic, so that it is bolted down, and basically when you have an earthquake, it won't fall through the ceiling and hit you in the head. And it also tells you a lot of other things, like you want to put flexible connections between the air handler and the ducts so it won't vibrate too bad. And how to do the drain. Having to tell somebody how to build it, okay, on your plans. And if you don't have good details, there's no telling, you know, they could just put, if I said put the air handler up in the attic, they could put 2 cinder blocks down here and drop the air handler on top of it and say, I'm finished. So you have to accurately, Tom would never do that, no. You have to accurately show the contractors exactly what needs to be built and what parts need to go on it and all that. Okay, this is what happens inside an air conditioner, like the heat pump at your house. Basically, you know, you've heard they say, oh, we blew the compressor in our air conditioner. Well, that is this thing right here, and it basically gets the refrigerant inside of it, and it pumps it up to a high pressure, and it gets real hot. Okay, so then here's some interesting ductwork in a restaurant that I did. And you know, you got to size every single piece of it. You got to size every grill. You know, they make 30 different grills of this size, you know, round grills like this. So you got to pick out the right one to make the air blow down properly. You don't want it blowing your papers all over the place, and you don't want it just whispering out so cold air won't get to you. So that's another component. And here it is, a heat pump, and it's called a package unit that goes on the roof. Everything is inside that box. You got the air handler and the condensing unit all inside that box. That's one right there. And those are called rooftop units. The other thing I do is design kitchen hoods. There's a big, huge exhaust fan that sucks all the smoke and grease out from our kitchen hoods. And mechanical engineers do that. They design the kitchen hoods and how much flow they need. That's a pretty dirty fan that I was looking at up on the roof, and that's what comes out of the kitchen hood. And so, see, I would select that fan to make sure it is powerful enough to get all the smoke and grease out of the kitchen. And I just want to let you know, there's all kind of different places that need air conditioning. Have you ever thought about how do they do air conditioning on submarines? It's not easy, but it's interesting to think about. Okay, when you get into bigger buildings, you can't, like if a hotel has 100 rooms, you don't want to have 100 of those heat pumps outside. That would be a nightmare to take care of. So it's this big machine, and it makes cold water. The pump pumps the cold water back and forth to all the different rooms and spaces, and so it goes to these things called fan coils, and each fan coil has a thermostat. So that's a chill water system, and the pump, that's a pump, and it pumps the water, and also it can pump hot water for heating from a boiler. So those are the condensing units on that job right there, that hotel. Those three things run that hotel, and those are big dog, condensing units for a chiller. So that's a commercial application. And that I got a picture of them lifting those things up to the roof with a big crane. So that was pretty cool. All right, geothermal. Geothermal is another way to do cooling, heating and cooling. And a lot of people think that you drill these wells and you suck the cold water out of the ground, or you suck the hot water out of the ground, and that's what heats and cools. That's not what it is. All these wells down here, and they're 300 feet deep, by the way. The pipe goes down and it does a U-turn and it comes back. And the whole system of wells replaces what the condensing unit does at your house, okay? It's just a place to dump the heat. So when they're cooling, the water's cooling off the compressor, right? And then the hot water goes down in the well, and the ground is like 75 degrees year-round. So if it's 100-degree water going down in here, it'll come back at 90 degrees. And that's how it dumps the heat into the ground. And it's as simple as that for a geothermal system. If you think about your condensing unit at home, it's the same thing, except for instead of dumping the heat into the air, it's dumping it into the ground. Any questions? Okay. Okay, this tells you, the ground is 67 degrees year-round, right where we are. I said 75, I was wrong. But, as you go up north, the ground gets colder. It's 47 degrees up in New York, and it's 77 degrees way down in Florida. So, it's not as good. Geothermal is not as good down here because it's very hot and the ground's warm. Remember I said one air conditioner gives you one thermostat? Well, if you have an office building that's 3 stories tall, and you have one air conditioner, who do you give the thermostat to?
The boss.
The CEO?
Yeah.
Well, that doesn't cut it with offices with 50, 60, 80, 100 people in the office building. This concept is called VAV. The cold air comes out of the air conditioner, and then each VAV box has a valve in it hooked up to a thermostat. So the thermostat says either I'm hot, open the valve, or I'm cold, close the valve. And also it's got a little heater in it too, which can give additional heat in the wintertime. So each VAV box gets a thermostat. So with one air conditioner, you can get an unlimited amount of thermostats, and that's a real popular concept for office buildings. That's a close-up of the VAV box. There's nothing but cold air in the duct that comes into it. So the only way you can get heating is this heater right here, and that will reheat the air as necessary. So, okay, this is the job that I designed. That's a VAV system. You have the air handler right here, and all the return air comes, this is all above the ceiling. You know, this would be above these lay-in grids. The return air comes in this big duct, goes back to the air handler. The cold air comes out, and it goes all the way around the building. And every so often it taps off and it hits a VAV box. So, you know, they'll upfit this building with cubicles all over, you know, and every, like all these cubicles, they have to share one thermostat. So, you know, that's a very typical design for an office building. Okay, this was a gym I designed for a school, and you can see the round ducts coming out. You know, in the gym, you got the big round ducts and the round diffusers coming down. Well, you look at that and you say, gosh, that's all mixed up and the lines are too close together. I can't see what's going on. How in the world does somebody build that? Well, if it gets too complicated, you got to do some more work. You got to do a section drawing and show it from the side. And this is just a decision you have to make, you know, to make it easy to build. To do the most cost-efficient air conditioner. That's a darn good question. Personally, for this area, I think it's a toss-up between a high-efficiency heat pump. That's the same thing at your house, but you know, on a building like this, you would have a bunch of them on the roof. It's hard to beat that, you know, because anybody can work on this, very simple. And they're not that expensive. It's a toss-up between that and probably geothermal, because although geothermal is very expensive on the front end, it lasts twice as long as a regular system, and it's substantially more efficient. The VAV is just more built for comfort. About, I'd say 3 weeks. And a lot of it is call the architect, ask questions, do what you can, wait on some answers, and pick it back up, you know. And I'm usually doing, like right now I've got probably 12 jobs laying on my desk. And I have to decide every day which one takes priority. And you know, what am I waiting? I'm waiting on all these things for this job. I'm going to set that aside. And this one's due in a week and a half, so I need to work on this one. So, you know, if they each take 3 weeks, you know, it's pretty tough to schedule yourself. So that's a big challenge. Yes, sir.
So if you had all the information at the beginning and there were no changes, how long would it take you for that building?
Okay, for that building,
Just
I could do
work.
that if the architectural drawings were complete.
Complete.
With all the information I needed, it didn't have any wheels on.
Right.
That means they don't change. Sometimes architects change things.
Never.
I could do that job in, if I didn't have anything else to do, I could do it in 1 week. Yeah.
Put all the stuff in, like, put everything in.
Oh, no, not install it, just
Yeah, that's why
design it.
how long does it
Oh,
take?
okay. All right. That building, okay, it would take You do the drawings, that takes 2 months. Then you submit them for permits, that takes another month. Then they go out for bids, that takes another month. That's 5 to 6 months there. And then that building would probably take 6 or 8 months to build, what y'all think? Okay, then they pour the concrete. Then structural comes in. Then it becomes a fight between plumbing, electrical, HVAC, and they're up in the ceiling fighting with each other on who gets to run their pipe, you know, where they want to run it before the duct man gets up there and steals all the space, where they got to run their pipes around it. So that's usually the way it works. What else?
Do you spend a lot of time on site or at all?
I spend about 90% of the time in the office and 10% of the time on the site. And that's a lot. I mean, that's a lot of being out. You know, if you think about one whole day every 10 days, you're gone on a job site somewhere. Yeah.
Why are you the only one smiling?
Oh, that's right, I need to go out there, right? Okay.
I'm the contractor, I guess, of architects, contractors, and engineers, and,
Tom is the one that started this whole thing. I want everybody to know that.
Thank you.
Credit for that. He and George got together, and they planted the seed, and they started this whole thing, and then they called me in, and